Hello and welcome to the session. In today's session, I'll be discussing with you about the sequential circuits and a particular sequential circuit which we formally call flip-flop. In fact, flip-flop is not a typical sequential circuit, but it is a result of it is utilized for creating many sequential circuits, but it is a circuit in itself. So we would be talking about the sequential circuits, and we will be discussing about something related to flip-flops. Well, first of all, we should look at the definition. A circuit, sequential circuits is a circuit whose output is dependent on the input and current state of circuit. So this is how we define a sequential circuit, whose output is dependent on the input and current state, and basically it's an interconnection of combinational circuits and storage elements. The storage elements, so flip-flop is primarily a storage element. Storage elements called flip-flops store binary information that indicates the state of sequential circuit at that time. So primarily flip-flop is part of sequential circuit and is a storage element. The second part of sequential circuits happens to be the combinational circuit. The combinational circuits are primarily the flow circuits, right? Now you must be wondering, like, what is the essence and what is the need of these circuits in computer systems? Well, let's look into the slide first and then we'll discuss something more. In certain situations, one need to remember the past state. So this is one of the important confluence. In certain situations, one need to remember the past state and move to the next state from there, right? So this is the one reason. Then these are useful for cases where a series of events to happen and storage of past information is useful. And an example of that situation is counters. Let me try to explain it further. How a sequential circuit is dependent on the previous state. Let's say a counter. So what does a counter do? It primarily does the counting job. So right now the counter is at, let's say, state number 5. Let's say it is a binary counter, so it is counting. So it is at state number 5. So it should move from state 5 to the next state, that is state number 6, right? So this particular circuit is expected to remember the present state, which may be 5 in the present state, and the future state becomes 6. Now for the further movement, it will then remember the state 6, right, and then move on to state number 7. And that's why, because it has to remember the state, what does it require? Definitely combinational circuit for change of state, but for remembering the thing you require a storage element, the flip-flop, within the combinational circuits. So this is within the sequential circuits. So sequential circuits in that particular sense is a combination of two things. Let us try to understand this particular situation a little bit more from a general life definition. Now most of us are aware about the traffic lights, right? Now a traffic light sequence moves in a particular way, from red to yellow and to once again green, okay? Maybe the red to green and green to yellow and yellow to red once again. Now this particular sequence, you once again need to remember the previous states, right? So flip-flops, or in fact not flip-flops, basically we need a storage element in this particular case, right? That what state this particular light, red light, is, and then a circuit which causes the change in the state at a particular moment of time. You must know that the traffic light changes after a particular specific period of time, right? So you require a circuit to do that particular activity, and a device or a circuit which stores that particular element, that what current state is. So I mean, wherever you require a typical sequence, you require a sequential circuit. That's what the name is, the sequential circuit. You move from sequence to sequential circuits. And what do you require? Once again, just the combinational circuit and the storage element. Now let's try to classify the sequential circuit in some sense. Well, there are two types of sequential circuits, in fact. So let's try to read the slide in this particular context. The sequential circuits are time dependent. First of all, this is very, very important thing. All sequential circuits are supposedly time dependent. Why time dependent? Obviously, you are moving from one state to another. So all these transitions have to take place at a particular time. Okay. The second point here is the sequential circuits are broadly classified depending upon the time at which their internal state changes. So this is an important confluence once again, and the two broad classification of sequential circuits are synchronous as well as asynchronous. So two broad, you can categorize synchronous, which have very defined time interval, and asynchronous, which can change state at certain point of time without, I mean, they can change state at several instances, right? Okay, now let's look into these definitions a little bit more. Synchronous circuits use flip-flops and their status can change only at discrete intervals, right? At discrete intervals, okay? A good choice of discrete digital device such as computer. So what we primarily focus in computer is synchronous circuits using flip-flops. Now, here I want to give you an example. Most of the time you used to wear watches earlier. There used to be a watch which used to move continuously, whereas in today's watch you will find the arm of seconds, which counts the second, moves 1 second at a time, whereas there was a continuous movement in certain cases. Now whenever you have a discrete moment, you are moving 1 second at a time directly, although the time elapsed is the same, but that is what we are talking about, the discrete, right? So at discrete step there will be change as far as flip-flop is concerned. Now when that particular change is going to happen? Well, for that you require a clock. But before that, let's try to look at asynchronous sequential circuits. Asynchronous sequential circuits may be regarded as combinational circuits with feedback. So certain feedback makes it, and they continuously change their state. Since the propagation delay of output to input are small, they may tend to become unstable at times. So this may happen. They may become unstable and they are not desirable for discrete digital devices like computers. Complex and asynchronous circuits are difficult to design also, and that's why we normally do not use these devices in computer. So what do we use? Synchronous circuits. But how the synchronization is achieved as far as sequential circuits are concerned? Well, let's look into those details. The synchronization in a sequential circuit is achieved by a clock pulse generator. Many a times you hear about this particular thing, which gives continuous clock pulse. A clock pulse can have two states, 0 or 1, disabled or active state. The storage elements can change their state only when a clock pulse occurs. Sequential circuits that have clock pulses as input to flip-flops are called clocked sequential circuits. Now, very important consideration over here is that most of the computers, we say, okay, this has clock speed of, let's say, 2 megahertz, 3 gigahertz, like that. What is that? That primarily is talking about the clock as far as sequential circuits which have been implemented in the computer is concerned. So faster is the clock speed. The faster can be your discrete states, the change rate of change of discrete states, and in turn that means that your instruction execution will be faster. Why? Suppose an instruction take 10 clock pulses, right, for execution, and if clock speed is faster, obviously your computer is going to execute the instruction at a faster rate. So this is all related to sequential circuit whenever we are referring to the clock speed into that particular sense. So from sequential circuits, then we move on to a very important component of sequential circuit, because combinational circuits we have already dealt with in one of the presentations. However, let's move on to one of the important circuitry requirement as far as sequential circuit is concerned, and that we call flip-flops. So what is a flip-flop? A flip-flop is a binary cell which stores one bit of information. One bit of information is stored. It itself is a sequential circuit. So it itself is a sequential circuit, but primarily utilized in storing of information. Flip-flop can change its state when clock pulse occur. But when? A clock pulse occur immediately then or at some point later? Generally, a flip-flop can change its state when the clock transitions from 0 to 1, this is called the rising edge, or from 1 to 0, this is called the falling edge, and not when clock is 1. Now this is a standard thing to use in a computer. If the storage element changes its state when clock is exactly at 1, then it is called a latch. A flip-flop is edge triggered. Edge triggered means either it is it changes its state when we are moving from 0 to 1 or from 1 to 0. And latch is level triggered. Latch primarily is governed by the level when the clock is stable at 1. So these are some of the things which we discuss as far as flip-flop is concerned. But flip-flop itself is sequential circuit, but one of the most important circuit as far as creation of devices or creation of devices in computers are concerned. And one of the most common device in computer system which you create is counter, because that keeps track of various states as far as counter is concerned. Now we first start with the latch, which changes its state when the level is there, or one level is there. So let's try to define the latch, and then we try to define the flip-flop. A latch is typically a combinational circuit. So let's look into the basic flip-flop latch. The one which is shown in the figure, this is called an SR latch, and it can be made either using NOR gates or it can be made using NAND gates. The one which I have shown here is being made with the help of NOR gate. Okay, so this is the basic latch which normally results into a flip-flop. But how does it store? But before we talk about that, let's look into what are the components of this particular thing, right? So it has two inputs. One is S, which is called the set, and the function of this set might be to set the output. And the output, there are two outputs which you can see here. One is Q, right? This is the main output, and Q prime, which is the complement output of the Q. So you have two input, S set and R reset. So the reset should make this particular output as 0. Set should make the output as 1. However, this particular flip-flop or this particular latch should constantly show a particular state. So that is very, very important. Okay, so output, in the case of output, if Q equals to 1 and Q dash equals to 0, the latch is in the set state, right? That's what we say. So if Q is 1, we are saying obviously Q dash in that particular state should be 0. We say that flip-flop is in the set state. So one state has been defined, set. The another state of the flip-flop happens to be if Q equals to 0 and Q dash equals to 1, then we say it is reset state, or in other terms you can say it is 0 in that particular state, but then you can always call it a reset state. So you have two states of this particular basic latch, and the first one is the set and the reset. Set is represented by a 1, the value of Q being 1. Obviously Q dash has to be 0 in that particular case, and reset state happens to be that the Q value is 0. But how does this particular function is achieved? Let's try to detail it with the help of another diagram of the same latch. So let's look into two things, like two tables are listed over here. The first, in fact the table at the bottom is the NOR gate table, right? This is the truth table for the NOR gate, right? So this truth table for the NOR gate, let's look into this particular situation. So suppose there are two inputs to NOR gate, let's say A and B, right? A NOR B will, if it passes through the NOR gate, what we will get? If the value of A and B both are 0, in an OR gate, what do we get? A 0, right? So in NOR gate, we will get a 1. Similarly, for value of A to be 0 and B 1, in OR gate, we will get 1. Therefore, in a NOR gate, which is complement of OR, we will get a 0. Similarly, for this case as well as 1 1 case, for OR gate, we are expected to get an output of 1, but for NOR gate, we will get these 3 as 0 outputs. So this basically, if there are 2 inputs A and B to a NOR gate, how the values will be resulted. And the typical symbol of NOR gate is with the complement, with the circle in front, okay, which represents that it is not OR. So this is the symbol. If we just forget this particular circle, then it is an OR gate. As soon as you put a circle here, it becomes a negation. So it is a NOR gate. Now let's look into what happens in the state of the flip-flop in this particular situation. Right. Do you see, or please notice this particular feedbacks. There are feedbacks from the output to the gates, right? So they are already there. So let's look into this particular situation. Suppose the value of S is 1, right? The set input is 1 and the reset input is 0, right? So look into this particular situation. So the reset input is 0. What is the value of set input? 1. Okay. We can go back to the slide, please. Put on the slide. Yeah. So what happens in this particular situation? The value of set input is 1. So one of the input to NOR gate happens to be 1. What will be the output? Irrespective of the other input, right? Irrespective of other input, you can see. If one of the input to the NOR gate is 1, the output has to be 0. So let's look into this. As soon as S becomes 1, right? After the basic propagation delay, you will get the value of Q prime as 0. Why you will get Q prime as 0? Because one of the input is 1, so automatically this Q prime is going to be resulting into 0 as per the truth table over here. At the same time, what you see here, this particular output, right? So the Q prime output, which is now 0, and what is the reset value at this point of time? It is shown over here, it is 0. So after the propagation delay, what is the value of Q prime? It has to be 0 because from the NOR gate it got converted to 0, right? So this particular value, so the input to this particular flip-flop, the top flip-flop, not flip-flop, my fault, this top NOR gate is R as well as Q dash. What is the value of Q dash? 0. What is the value of R? 0. What should be the value of Q? It should result into 1. Okay, what is the state of flip-flop then? Q is 1, Q dash is 0. What is this state? This is a set state. So as soon as you applied S as 1, what is the result? The flip-flop is in set state, right? So flip-flop gets converted into set state. Now the flip-flop will remain in set state even if we move S to 0. Let's try to do that particular situation. So now S moves to 0. R was already 0, so that is fine. So flip-flop should remain in the set state. Then only we can assure, or we will be assured of that this particular flip-flop is still in set state, so it is maintaining the state, or in other words, it has become a storage element and it is remembering 1 in that particular sense. So let's try to identify the states based on that. So what was the value of Q? Q is 1. This previous value of Q is 1 now, right? Okay, so Q is 1. So this particular, one of the input to the bottom NOR gate is 1, right? So even if S goes to 0, what is the input to this NOR gate? 1 as well as 0. So we get an input of 1, 0. What should be the output? 0, right? So this output 0 is once again is to this particular NOR gate, right? And R is already 0, so this particular the output, that is Q, will remain at 1 once we go back from S from 1 to 0. So could you see this particular fact that your state is not going to change even thereafter that the S input after from set state has gone back to 0. Now take the factor of R. Now R goes to 1, right? Now as soon as R goes to 1, what happens? We are assuming that Q was 1 and Q dash was 0. Even if we don't assume these two, it doesn't matter. So let's say R goes to 1. As soon as R goes to 1, irrespective of the Q dash value, what is the input to this particular thing? One of them is 1. That means the output of the top NOR gate, that is Q, now will become 0, irrespective of the value of Q dash. In our case, the Q dash was 0, so you can see 1, 0, we are getting a 0 as output. So Q becomes 0. Okay? As soon as Q becomes 0, S was already 0, so 0, 0 is applied to the bottom NOR gate, and what is the output in that particular case? 0, 0. It should get converted to 1. So what you get? The state as the Q value is 0 and Q dash value becomes 1. And what happens? That is, this is the reset state. The flip-flop Q has moved to 0. So this is how this particular latch is operating. Once again, when we come back to the state of 0 and 0, nothing happens, because this is exactly, you can try that particular thing out, nothing will happen, and the flip-flop will remain in the reset state which it had acquired at this point of time. Now what will happen if both the input goes to 1? Well, that is a very unstable state for this particular basic RS latch, right? Or SR latch, we call it SR latch. So that is a very unstable edge, and that is why it has been shown in red. That is an undesirable state as far as this basic flip-flop is concerned. So what you could see, and what I have tried to explain to you, how the state, like how beautifully with the help of certain feedbacks, right, we are able to demonstrate a storage element in a computer system with the help of total electronic circuit, right? So a typical computer system, you can find this particular situation where everything can be represented, okay, electronic circuit, and that electronic circuit is beautifully utilized not only for flow of information, that is a combinational circuit which basically causes change of state, but the same thing with a little bit of feedback causes you to store the information in a slightly just modify the circuit and it becomes a flip-flop. So a flip-flop is a sequential circuit in that particular term, yet it is made up of combinational circuit with the feedback loops, right? So it is, very interesting situation. Okay, so this was fine. This was a basic latch. It can change its state any point of time. The problem which may find that the circuit may become stable. It can loop. So that's why we need a clogged SR flip-flop. So we need to bring the element of clock, right? So this was the basic latch. You can see the basic latch over here. So we keep that particular basic latch as it is. But in addition, we involve two more AND gates which basically controls the input of R and S to these particular to these NOR gates. Okay, the R will be applied only on the occurrence of the clock pulse, right? So is the value of S. So our basic function which we were stating remains the same, right? But what will happen in this particular case? In this particular case, the inputs will be applied. The input value of R and S will be applied on the circuit only when a clock pulse occurs, right? So this is a clogged SR flip-flop, all right? we are not going to discuss the edge triggered kind of flip-flop, but the SR flip-flop, like even if you know this much, that itself is a good example of how flip-flop functions. Now, how flip-flops are represented? The graphical symbol of SR flip-flop is represented here. The arrowhead symbol in front of the clock pulse C indicate that the flip-flop responds to leading edge, that is 0 to 1, when the from 0 to 1 of the clock pulse, or the rising edge, right? So there is a the leading edge symbol over here. So there are two inputs, R and S. We have Q and Q prime. In this particular case, we had actually put a bar, which may be visible very closely. Okay, so we have R and S as two inputs, or S or R set as well as reset as the two input, as well as clock, and this flip-flop will respond when the leading edge or the rising edge, at the rising edge of the clock pulse, and you get the output as Q as well as Q dash. So this becomes the graphical symbol as far as this particular SR flip-flop is concerned. So this, I mean, whenever we are trying to draw circuits, this particular graphical symbol is to be utilized. Now, is there any other information? Let's look into this logical diagram was already we have gone through, but let's look into the characteristic table for this particular flip-flop. When there is no clock pulse, right, irrespective of the value, in fact, even if the clock pulse is 1, right, and the value of S and R happen to be 0, 0, what will happen? The next state of the flip-flop, QT plus 1 basically defines the next state of the flip-flop. Okay, and QT defines the present state of the flip-flop. Okay, so if the value of S and R are 0, 0, the QT, that is QT plus 1, that is the next state of the flip-flop, will remain to be the present state of the flip-flop. And that was the discussion when we said that the flip-flop, after the R and S moves to or S moves to 0, right, the flip-flop remained in set state. Similarly, for the reset case, we found out then even if the value of R moves to 0, the flip-flop remained in the reset state. So that is what it means. No change in state, right? So if it is 0 and 0, no state in change. The clock occurs or does not occur. It does not matter in that particular case. So it can be 0/1 in that situation. However, now these two things represent, first one represents the reset state. So what happens? A clock pulse occurs, S value is 0 and R value is 1. So on the occurrence of clock pulse, the flip-flop goes to reset state. That's what we saw in the latch, right? So it goes to the reset state. That means the value of Q becomes 0. That's what we observed. And the value of Q dash becomes 1. All right. So you can try that particular thing out here, and it should work out in exactly the similar way. And then we have the similar thing for the set state. Please put on the slide. The set state also, once again we have the same 1, 0, it becomes set, and finally this particular 1, 1, when R, S and R both goes to 1, it is an undefined state. We don't know based on which flip-flop come or what happens inside. We don't know about this particular state. So for this particular flip-flop, what we have defined, SR clocked flip-flop, the state of S, if both of these values goes to 1 and 1, it is not defined. In fact, it is then our responsibility that if we are using this particular flip-flop for designing the circuits, we make sure that that 1, 1 state doesn't occur. Because if that particular state occurs, we don't know what state of state this particular flip-flop will be after that. In discrete computers, we always want to know what is going to be the next state and what is the present state. And that is the basis of designing circuits also, right? So let's try to summarize the SR flip-flop operations. If no clock pulse, no clock signals, that is C is equal to 0, then output cannot change irrespective of R and S values. When clock pulse changes from 0 to 1 and S equals to 1, and R equals to 0, then output becomes Q is equal to 1 and Q dash equals to 0, that is set state. When R equals to 1, S equals to 0, this reset input has been set, and clock signal C changes from 0 to 1, then output is we get a reset state, which means Q is 0 and Q dash is 1. And during positive clock transition, if both S and R becomes 1, then output is not defined, as it may become 0 or 1 depending upon the internal timing delays occurring in the circuit, and that's why we don't want this condition to occur within a flip-flop system. Now, so this is one particular flip-flop. There are not just one flip-flop, there are many more flip-flops, right? There is one D flip-flop, there is one T flip-flop, and another one JK. Will be leaving something for you for reading now. Once you are clear about this SR flip-flop, you will be able to make out other flip-flops also, because the circuitry is just mild variation of this particular state. However, I'll just explain you the JK flip-flop a little bit more. The JK flip-flop is a modification of SR flip-flop, right? The one which we had. It has two inputs like S and R, and all possible input combinations are valid in JK flip-flops, including 1, 1. The inputs J and K behave exactly like input S and R to set and reset flip-flops, right? So J is S and R happens to be K respectively. When J and K are 1, the flip-flop output is complemented with clock transition. So what we do in this JK flip-flop, we have enhanced the circuit, right? We have enhanced the circuit a little bit further, and in this particular circuit, even if the value of J and K becomes 1, even then the state of flip-flop is still defined. Okay, the graphical system this time it should be JK flip-flop. Of JK flip-flop, once again, is J and K are there. The clock input specify the leading edge, Q and Q bar. So it's almost the same. And the graphical logic diagram for this particular input, you please notice there is another feedback coming in to the AND gate, all right? And that actually results. Why don't I would like you to try this particular thing out, that when Q, okay, you can try that particular thing out. Let's say when J and K, both values are 1, okay, and we assume the value of Q at that point of time is also 1, all right. So how the situation will happen? So you have 1, obviously Q dash is 0 at that point of time. So, and the clock pulse occurs. So what are the values? This is 1, K is 1, and the clock pulse is 1. So what is the input on this particular side? 1, right? So this basically represents your R, right? So this reset value is 1, right? Reset value is 1, whereas J is 1, whereas Q dash is 0, so this is 0. So what you get as input, that you get K value as, that is K is the reset value as 1, and S, which is the J value, which is set value, is 0. So you get 1, 0, and 1, 0 primarily does what job? 1, 0 basically will this is J and K. So 0, 1, this is the situation. So this reset, it is going to reset your flip-flop. That means Q from 1 has moved to 0. Isn't it a complement state? Exactly, that's what we want to say. So similarly, you can try for, if the value of Q is 0, you will get the other way around. Like this value will become 0, that is R value is 0, and this particular value will be 1. So by little bit modification of circuit, right? And this is what the smart thing about electronics is. A little bit modification of circuit, and you have utilized the flip-flop last input also, and that particular thing is going to result into complement state. So if the Q was 1, when you say J and K both becomes 1, in the next state Q will become If it was 1, it will become 0, but if it was 0, it will become 1, and Q dash accordingly changes as per the requirement. So this is, I mean, the JK flip-flop. Once again, I would like to say, little bit modification, little bit use of your logical analysis, and you are able to bring in something very, very interesting situations as far as flip-flops are concerned. So flip-flops are very important devices as far as construction of your sequential circuits are concerned. Why? Because they are able to store information. The combinational, and storage is, once again, storage is also through the flow, but then a consistent state gets applied, and that's how with the help of AND, NOR, NAND gate only, right? These are all flow circuits, combinational circuits, but then those combinational and feedback kind of thing results into storage of information, and that's a very, very, in fact, that actually resulted into the development of these discrete devices, and this, you see, where are we now? Okay, now one more thing we want to define about the flip-flop, and that particular thing is called excitation tables. Now, you must be wondering about, we talked about the characteristic table, right? So what the characteristic table of flip-flops do? They provide the next state information. So what will happen if inputs, like input of S and R goes to this particular stage, right? But they are not particularly useful for analysis, right? These tables are useful for analysis of sequential circuits, but not for design, right? So, but for the design process, you need to know the required flip-flop input. What input should be put into the flip-flop for the required transition from present state to the next state. So this is a very important, like when you might be doing a counter design, this information is more important, like what input should be given to the flip-flop, okay? So that it moves to the next desirable state as per desired by you. So transition from present state to the next state, how you can achieve that. Such a table is called or is known as excitation table. So that's why do we want to know about excitation table? Because excitation table is a very important table for us from the design point of view. Not if analysis is to be done of as far as circuit is concerned, the characteristic table is very, very important, the one which we used QT plus 1, SR value changing. But let's look into the excitation table. So what way we will go through? We'll first see an excitation table. This time we will see it for JK flip-flop, and then we'll try to define how we have arrived at this particular table. So let's look into the excitation table for JK flip-flop, where we are defining QT and QT plus 1, right? Please focus on this. Yeah. Please focus on the slide now. You can look into J and K as two inputs. Now what would be these two values? So if I want to move from the present state, which happens to be QT, to the next state QT plus 1, once again 0. So if you are into a reset state, you want to remain in the reset state, that means a 0 is stored in the flip-flop. What do you require? The value of J should be kept as 0, and the value of K should be anything, either 0 or 1. The symbol of X in the table means don't care condition, that it doesn't matter whether input is 0 or 1. But how do we arrive at this? We will come to that. Then if I want to move from 0 to 1, that is, I want to move from reset state to the set state in the flip-flop, what input should I apply? The value of J, which is the set input, should be set to 1, and the value of K doesn't matter. What does it mean? Once again, we would like to see that. And so is the case when I want to move from reset state to 0, X 1. Okay, from 1 to 1, doesn't matter, don't care, but you have to put a 0. But how do we arrive at these things, table? That is the major thing, right? So how do we arrive at this particular important information, right? So let's look into that. How to make excitation table for JK flip-flop. The state transition from the present state. Now this is for 0, 0. Okay. So the state transition from present state 0 to the next state 0 can be achieved when J equals to 0, K equals to 0, right? So no change of state. That was the characteristic table. When J equals to 0, K equals to 0, no change of state. You don't have to do anything. Or the second way, that the reset input is applied as 1. So if that is K, so the reset input is put as 1, even then flip-flop will be brought to 0 state, whatever state it was. So even if it was 0, it will remain in 0. So if I put J as 0 and K as 1, then flip-flop will be reset, flip-flop resets. That is, it will be in state 0. So what does it tells me? The value of J has to be 0, but the K can be 0 or 1. That is X, don't care. The value of K does not matter. It can be 0 or 1, but the value of J has to be 0. Then the flip-flop will necessarily remains, and if it is in the present state 0, it will move to the next state will be once again 0. Let's see this, the similar situation, the state transition from present state 0 to next state 1. Now to do so, there are two ways of getting it. What we do, either we simply set, right? So either we set the flip-flop or we complement the flip-flop, right? So two possible ways for GK. So what we are doing, setting how we are doing, J is the set input. So we apply J as 1, K as 0. So what will be the next state for the flip-flop? It will be in the set state. So we reach from 0 state to 1 state. On the other hand, if it was in the state 0, if I apply J equals to 1 and K equals to 1, the flip-flop will be complemented and we will move from 0 to 1. Why? Because it's a complement. So we want to complement the flip-flop and that will happen. So this is the way. I'm sorry, just slip here. So this is the way what you can see. The flip-flop will be complemented. Thus, the value of J has to be 1. And the K does not matter, so that is don't care, and that is X. So you can see that this particular thing we will be able to achieve. Then the next, okay, now in this particular case, we are assuming that we were in state 1 and we want the next state to be 0. How we can get that? We reset the flip-flop, right? So we get that, or we complement it. So that's what you see in this particular case. The J value can be 0 or 1. K value has to be 1, and that's what you see in this particular situation. And the final case, what is the final case? When you want to, when the present state is 1 and next state you want 1. So that means you want no change. So J and K value has to be 0, 0, or in the other situation, you just set the flip-flop. So you just apply the value of J as 1 and the value of K as 0, then flip-flop is set to 1. So what we say in this particular case, K value has to be 0, but J can be 0 or 1, that is X. So finally, if I want to sum up the whole process, what we are trying to say, the present state of the flip-flop, okay, the next state 0, the JK value should be 0 and X, and this is how we come up to this particular J equals to 0, K equals to 0, J equals to 0, K is equal to 1. This is the way we come up. This is exactly what I have explained to you in all the 4 steps. So go through this particular thing very meticulously and you will be once again able to make out what way we are generating the excitation table. So in this particular session, I have tried to define very basics about the sequential circuits. But what is my basic objective initially was to explain to you what are the basic issues as far as sequential circuits are concerned. Where do you want to need that particular sequential circuit? And then we talked about one of the major component of any sequential circuit, which can be utilized as the storage element within a sequential circuit. So that was the flip-flop. And in flip-flop, we talked about 2 situations. One, how exactly it functions, and the characteristic table for its functioning. And the second thing we talked about, the excitation table for the flip-flops. And the use of excitation table is going to be when we are going to utilize the flip-flop for the design purposes. So for the time being, I wind up this session with this particular statement. Thank you for coming for the session and see you later on. Bye.